Hi everyone, welcome back to Math 361. This is Scott. Let's get started. What we're going to talk about today is section 1.7, in which we will be making our first introduction to a topic that will be of great importance to us over the course of the course, and that topic is linear independence. So first off, let's talk about what we are working with here. So a setup is we have a collection of vectors, v1 through v, let's say, n. Right, so we have n different vectors here. Actually, let's make it v1 through vp, just so we're matching the notation that's used in the book. So a collection of p different vectors, v1 through vp. Now, this collection is linearly dependent if this is true. The collection is linearly dependent. So the opposite of independent is dependent, and that's what we'll define first. If. Now there are a couple ways we can word this. The first way is any one of the vectors can be expressed as a non-trivial linear combination of the others, which in turn is equivalent. So if we have, let's say, v1 is equal to 2 times v2 minus 3 times v3 plus 4 times v4 minus 7 times v5 plus 1/2 times v6, etc. Then what we could do is we could rearrange everything. So we move everything to one side and just have 0 on the other, and this will be the more common way we'll express this. So the second way of expressing this would be there is a non-trivial linear combination of the v's, or the vi is a way we can refer to the whole class of the vi that makes 0. So in other words, i.e., there are C1 up through CP. They're not all 0, that's what makes it non-trivial. Not all 0, and it's just 0 the number, not 0 the vector, so that's out of there. Not all 0. Such that C1 V1 plus dot 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 up to CP VP. So the V's are vectors, the C's are scalars. Those all add up to make the 0 vector. So that's what it means to be linearly dependent. If a collection, on the other hand, is linearly independent, then that means that this cannot happen. So the collection is linearly linearly independent as opposed to dependent if. So one way of putting it is no. So no one of the vectors, or none of the vectors, is a linear combination of the others or two, another way of putting that, if there is a linear combination C1 V1 plus dot 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 up to CP VP, which comes out equaling 0, then all of the CI must be 0. There's no other way to make 0 other than 0, 0, 0, 0, 0, 0. So what that means is, so thus, the V's, V1 up through VP, those are linearly independent, if and only if the vector equation x1 v1 plus dot 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 up to xp vp equals 0 has only the trivial solution. But wait, what does that mean in terms of things that we've already seen before? Well, that means that we can set up this vector equation into the usual matrix, the augmented matrix, and we can go through the steps of trying to solve that. So therefore, if we construct the augmented matrix so it's going to be V1 up through VP followed by 0. So these are each column vectors, so these are the columns. So just remember, these are all column vectors here. So these are talking about the columns of the matrix. So if we construct this, then row reduce, we won't get any free variables. So if we do get free variables, then what that means is that we have actually a way, we have a recipe for making the V's equal 0. If there are any free variables, And if there are any free variables, i.e. columns without a pivot, then there is a combination of the VI, which is a non-trivial combination, of the VI that makes the zero vector. And in particular, we can find such a combination by picking any non-zero values for the free variables. We can find such a combination by choosing any non-zero values for the free variables. We can then rewrite the relation to get one of the vectors as a combination of the others. Okay, so that's a lot of writing words, which is, not the custom in a lot of math classes that you've had before this. But now let's see what this means if we actually try to do this as an example. So as an example, this will be the first. We're going to do a couple examples. One where they turn out to be linearly independent, and one where they turn out to be linearly dependent. So let's take as an example something like this. So are the following linearly dependent or independent? And let's take as an example first the vectors 1, 0, 0, 1, or sorry, let's say 2, 1, 0, and then finally 3, 2, 1. So these are our three vectors: 1, 0, 0, 2, 1, 0, 3, 2, 0. Or sorry, 3, 2, 1. So now the question is, are these vectors linearly independent or dependent? So what this comes down to is a question really about the augmented matrix 1, 0, 0, 2, 1, 0, 3, 2, 1, augmented by zeros. And the question is whether the system that we create here is going to be one that involves pivots everywhere and all the variable columns, not counting this one, or is it one that does not? So right here we can see that that in the x1 column, x2 column, and x3 column, we can see that there are in fact pivots everywhere, and without even row reducing it, any further because right now it's not in reduced or echelon form, but it is in echelon form. We can see that there's a pivot everywhere, which means that all the variables are basic, no free variables. No free variables. The vectors, therefore, are linearly independent. So that's the first example. Now let's try another example where the vectors in question will be 1, 2, 3, 4, 5, 6, and 7, 8, 9. So these vectors here are they linearly dependent or independent? In other words, can any one of them be written as a combination of the others? Is any one of them redundant, is another way of putting this. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then to answer this question, we augment a column of zeros and we row reduce. Now, we can row reduce this. It won't take very many steps to do it by hand, but we can also just use a calculator, or we can just, or you can just take my word for it. The row reduced version of this. So we row reduce, and take it from me, what you get is 1, 0, negative 1, 0, 0, 1, 2, 0, and then 0, 0, 0, 0. So, looking at this, this is in reduced or echelon form now. And what we will have is, if this is x1 and x2 and x3, we are going to have a free variable, and that free variable is x3. Now that already answers the question whether these are linearly dependent or independent, but if there's a further follow-up and we want to find a linear dependence among them, then this is what we do. So the x3 is free, which means that they are linearly dependent. But we can actually go further than that, and we can say x1 plus negative x3 equals 0, which means that x1 equals x3. We can say x2 plus 2x3 equals 0, which means that x2 is equal to negative 2x3. And of course x3 equals itself. So then what that means is that if I set x3 just equal to anything, it can be equal to 1 or 2 or anything, just don't use 0. So if I set x3 equals 0, then x1 will equal, so if I set x3 equals 1, then x1 will equal 1, x2 will equal negative 2, and x3 will equal 1. Which means then, here is a linear combination of the three vectors that will equal 0. So 1 times 1, 2, 3 minus 2 times 4, 5, 6 plus 1 times 7, 8, 9 will equal 0. Or if I am interested in writing it as as one of the vectors in terms of the other, so this is a linear combination that equals 0. So that's what this is. Or I can write one of them as a combination of the other by just basically solving for it. Or I can rewrite, and I can have 1 times 1, 2, 3 is equal to 2 times 4, 5, 6 minus 1 times 7, 8, 9. And this gives a one vector as a combination of the others. Now, geometrically, what this means, so we won't write this down, but we'll just say it. Geometrically, what this means is that if you have any two of these vectors and you make the plane out of them, the third vector will be part of that plane already. So what that means is although there are three vectors here, together, all the linear combinations of them, it turns out that one of them is redundant, and so all the linear combinations of them are just a two-dimensional plane. What that means is we have one vector that is redundant in the set, and it can be actually any of the three vectors. We could take it out, and we would still have the same basic plane, because one of them can always be written as the linear combination of the other two. Now, here's a theorem that will help us in the task of determining linear dependence or independence. And it's because it's going to be coming up a lot, in fact, so it may seem like a very abstract notion, and in some ways it is, but it'll be a very important subject for us, and actually even in Math 256 it'll be an important subject. So here's some things that will help us in the way of figuring out when things are linearly independent or not. So if we have a collection, if we have only one vector in our collection, I should say, if we have only one vector in our collection, the collection is linearly independent unless that vector is 0. So the vector has to be 0 to begin with in order for the set to be linearly dependent. Otherwise, just a single vector, it can't possibly be redundant. It must be independent unless the vector is 0. So if we have a collection of two vectors, they are linearly independent if and only if Neither one is a constant multiple of the other. I should say here, so technically this is covered, but I should say two non-zero vectors, because otherwise it'll be, otherwise you may be fooled, because 0, 0, 0 doesn't look like a multiple of 1, 2, 3, for example, but it is. It's just a multiple by a factor of 0. But here, but we don't need, but that's technically already covered in the statement, but we just want to be extra clear. And then 3, if there are more vectors, in a collection, then entries in each vector, the collection must be linearly dependent and the reason is you can't possibly have all of the variables be basic variables if you have more columns than you have rows, because you can only have, if you have, say, 5 rows and you have 7 columns, you can only have up to 5 pivots, so not every column gets one. And then the last one here, any collection that contains 0. So any collection of vectors that contains the 0 vector contains the 0 vector is linearly dependent. So this gives you a nice short little way to determine whether vectors are linearly dependent or independent. Let's try an example here. Linearly independent or dependent. And then what's going to follow is a collection of vectors, and it's up to us to make the determination. So for the first one, let's just take a little collection here that contains, so the squiggly bracket here indicates collection. Let's say 1, 2, 3. So just a single vector, 1, 2, 3. Well, according to the theorem, if we have a collection that only has one vector in it, and that vector is not the 0 vector, it's linearly independent. That's by part 1 of that theorem. Let's say we had B, a pair of vectors, 1, 2, 3, and 3, 2, 1. Now looking at this, it's clear that this is not a multiple of that and vice versa. For this to be a multiple of that, it would have to be, so 1 times 3 makes 3, and that doesn't match the other two. So it's not a multiple of the other, neither one is a multiple of the other one, so therefore they are linearly independent by property 2. These are linearly independent by property 2. Let's say now we have something like this. Let's say we had 3 vectors, each with 2 entries. 1, 2, 0, 1, 1, 1. So what we've got here is a nice little situation. 3 vectors, each with 2 entries. Are they linearly independent or dependent? Well, without even giving it any thought at all, I can immediately jump to a conclusion, because there is no possible way, when I made an augmented matrix with some zeros on the right here, there's no possible way I'm going to get a pivot for each of my 3 variables, because there are only 2 rows in which pivots can even appear. So by property 3, we've got here a linearly dependent set. Linearly dependent. By property 3. And then lastly here, obviously you can see the way the wind is blowing, I'm going to be doing something that is going to be an illustration of property 4. So what that means is we're going to have a collection of vectors. Let's say 1, 2, 3, 3, 2, 1, 0, 0, 0. And here we've got the 0 vector amongst our collection, therefore our collection is linearly dependent. Okay, so this is just a working example of each of the 4 properties in action. Alright, well, as I said, this is a topic we'll be coming back to over and over again throughout the course of the course. And so as we build up more know-how, we will build up more sophistication, and we'll build up more properties of use to us. So as that happens, we'll be returning to this topic. But for now, that's going to do it. So until the next episode of Math 261, bye.